This video is covering fitting a model to a bivariate data plot. The first thing we're going to look at is fitting the model. So that's just identifying the equation of the linear model. Then we're going to explain what that equation means in words, so put the equation into context. For merit, we need to justify the model. So that's visually looking at the model and seeing whether the line of best fit adequately explains the data. And one way to get excellence is to explore other models. So I'm going to give a couple of examples of exploring a quadratic model. So in the first example, we've got athlete's weight versus height. So fitting the model is just getting the equation of the line of best fit. So the line of best fit is the red line, and the equation for that line of best fit is given on the top left of NZ Grapher. So the equation is quite simply that the weight equals the 1.12 times the height minus 126.2. We then need to explain what that equation means in words. So for every 1 centimetre increase in height, on average we're expecting an athlete's weight to increase by the 1.12 kilos. So it's really important we use the correct units here. So for every 1 unit increase, where the unit is 1 centimetre, how many units do we expect, where units is kilos, the athlete's weight to increase by? So just going into a little bit more detail. So if I had an athlete that was 170 centimetres tall, I could go up and I could read that equation of the line of best fit, and I could read across and I could say that I'd expect this 170 centimetre tall athlete to weigh 64 kilos. If I had another athlete that was 190 centimetres tall, I could go up and off the line of best fit I could see that I'd expect them to weigh around about 86 kilos. So for every 1 centimetre extra tall they are, on average I'm expecting them to be 1.12 kilos heavier. So this 1.12 kilos is just the coefficient of height, and so because it's a positive number, that means this line of best fit is sloping up, and we're expecting an increase in the athlete's weight. For merit, we need to justify our model. So justifying the model is answering the question, if you tell me the athlete's height, how good is our model at predicting the weight? So we're going to consider a few different things. The first thing is we can consider them across the whole model, or we could break the model into sections and consider the model in parts. So the first question is the linear trend appropriate? So do the data points follow a linear pattern or a straight line, or is a curved line of best fit going to be better? The second feature is looking at the strength of the relationship. So the stronger the relationship, the better our model is at predicting the weight. So the stronger the relationship, the closer the points are to the line of best fit, and the better our model is at doing its prediction. The more data points, the more certainty we have in the model. So the more data points that are used to create the model, then the more certainty we have that our model is correct. So if we look at the heights, say below 160 centimetres, there's not very many data points there. So if we look at this part of the model in isolation, we can say there's not very many data points down here, so we have less certainty that our model is correct down the bottom. There should be no patterns within the data points that are not explained by the model. So this plot, there are no particular patterns, but in another example later on there's going to be definite patterns, and we can see why they make the model inadequate. The data points should be evenly distributed above and below the line of best fit. So what that's saying is the line of best fit should go through the middle of the data points, and there should be an even amount of data points above and below the line of best fit, and therefore the line of best fit won't have any bias in its prediction. Lastly, we could ask the question of what range of explanatory variables or values is our model going to make reliable predictions. So visually, if I looked at this plot, I could say that our linear model appears to fit the data well. If it didn't fit the data well, we could say that it fits the data adequately, or we could say that our linear model has some weaknesses within it. This is supported by the data having a strong linear relationship. So we're going back to the features of the data and we're using those to support whether we think the linear model fits the data well or not. There are no patterns within the data points, and they're evenly distributed above and below the line of best fit. There are, however, fewer data points for heights below the 160 centimeters, and so for these heights that are below the 160 centimeters, we're saying that the model is not going to be as good for these heights. In the next example, we have marathon time versus stride length. So we need to fit the model. So again, that's just reading the equation of the line of best fit. We want to put that into words. So for every 1 centimeter increase in stride length, on average we expect marathon time to reduce by the 1.87 minutes. So because the coefficient of stride length is a negative here, that means we're expecting marathon time to reduce, and we can see that by the line of best fit sloping downwards from left to right. We then need to justify our model. So again, we're looking at the same things as before. So we're looking at the features, whether it's linear or not, whether it's strong or not. We're looking at the amount of data points. So the more data points we have, the more certainty we can have in our model. We're looking to make sure there's no patterns within the data points that are not explained by the model. And we want the data points evenly distributed above and below the line of best fit. And we will also break the model into ranges if we'd like to. So for this one, we can say that visually the linear model appears to fit the data well. This is supported by our data having a strong linear relationship. There are no patterns within the data points, and they're evenly distributed above and below the line of best fit. And there's an adequate number of data points spread along the range of values. So what I'm saying here is overall, I think that this linear model appears to fit the data well. However, we could use the same plot and we could look at it in a little bit more detail. So here for the really low stride lengths, we can see there's more data points above the line of best fit than the below the line of best fit. So we want the same amount above and below. And also for the very high stride lengths, there's more data points above the line of best fit. You can't really see it, but there's quite a few data points actually on top of each other there, but there's more data above than below. So if we look at that in more detail, actually a curved line of best fit might represent this data better. So just bringing this data plot onto NZ-Grapher, we've got the linear plot here, and we can see there's more data points above than below. And again, for this is for the high and the low ends of stride length. So we can take the regression line off, and we can put a quadratic best fit line, and we can see that actually improves the fit here. So the data points are evenly distributed above and below the line of best fit. And so what I'm saying is the quadratic line of best fit might actually be better than the linear line of best fit. But in actual fact, if we look at the line of best fit, overall, if you looked at the amount of data points, the features of the graph, the patterns within the data points, or lack thereof, and the distribution of the points above and below the line of best fit, I would say that the linear line of best fit is adequate for representing this data. So the question is again, if you gave me a particular stride length, how good is my model at telling me what the marathon time or predicting what the marathon time would be for a person with that stride length? And so I'd say this model, the linear model, is adequate, but for excellence we may want to go and have a look at the quadratic line of best fit, and we could come to the conclusion that that's better. But for this data plot, there's actually not that much of a difference between the two models. The last example is diamond weight versus price. So this one, we can see that actually the linear model probably isn't very good in this circumstance. But for a start, we're going to fit the model. So that's just the equation of the line of best fit. So the line of best fit in the equation that's given. We're going to put that into words. So for every 1 carat increase in the diamond's weight, on average, we'd expect the price to increase by the $7,788 US. But let's have a look at justifying the model. So again, we're going to look at the features. We're going to look at the amount of data points, the patterns or lack thereof, the distribution of the points above and below the line best fit, and we can break that into ranges. So for the features, we can see that the linear line of best fit probably isn't appropriate, and the data points aren't following a linear pattern. That's more of a curved pattern. We're wanting the data points to be strong, so close to the line of best fit, but we can see as weight increases that the strength of the relationship is getting weaker, and in actual fact when the diamonds weigh around about 1 carat, there's quite a large variation in prices, and so when the diamonds weigh quite a lot, the model isn't very good at predicting what the price is going to be. The amount of data points is probably the only thing that's really good about this graph. There are a lot of data points and they are spread evenly along the range of weights, but there's definitely some patterns within the data points here. So if we look at the low weights, the pattern isn't being explained by the line of best fit. So for a start, they're above the line of best fit, then they're below the line of best fit. And so there's different patterns there. We want them to be evenly distributed above and below the line of best fit. In actual fact, when the weight is below 0.5 carats, this is the actual or the observed prices of the diamonds, and so this is the estimated price, and so the estimated price is always underestimating the price of the actual diamond for these low weights. So let's go down and see what we're going to say about this graph. So visually the linear model appears to have some weaknesses. The trend appears to be non-linear, so because it's non-linear, then the linear line of best fit is probably not good. So a non-linear just means it's not in a straight line, it's more of a curved line. And the relationship is getting weaker as the diamond's weight increases, which means that the linear model is getting worse at predicting the prices of the diamonds as the weight increases. There are patterns within the data points, and they're not evenly distributed above and below the line of best fit. So this is really bad for saying that the linear model is good. And this is particularly bad when the diamond weights are less than the 0.45 carats. We can also say that the line of best fit tends to underestimate the diamond price for weights below the 0.3 carats. So the line of best fit is below the actual observed weights. And the only really good thing is there's an adequate number of data points spread along the range of diamond weights. So let's have a look at this data in NZ-Grapher. So this is the linear plot, and we're saying the linear line of best fit isn't very good, so we can take that off. We can fit the quadratic line of best fit, and we can see that the quadratic line of best fit goes more through the middle of the data points. So the data points are more evenly distributed above and below the line of best fit. We can see that the patterns within the data points are being explained better by the quadratic line of best fit. And so the linear line of best fit didn't explain the data very well. And although there are still some patterns, we can see that here the data points are consistently below the line of best fit. On average, I think that the quadratic line of best fit suits the data better than the linear line of best fit. So that was an introduction to fitting a model to a bivariate data plot.